So please recall that lowest pKa means most acidic. And for acidity, we need to think about trends like resonance, which is often important, like size. Electronegativity is another trend. And then the electronegativity of nearby atoms, or induction, inductive effect, is a final factor. So my thought is that the carbons with hydrogens are probably going to be least acidic. So these carbons are small and they are not electronegative and they do not have a great deal of induction. But to answer this question, you know something about pKa. So the first comparison I see is a very electronegative atom, oxygen, versus a very large atom, sulfur. And when you're comparing two acids in the same column, where sulfur is larger, the sulfur or the larger atom is more acidic. Thiols have pKa's around 8 or 10 because of size, and that beats the high electronegativity of oxygen, only because it's a fair comparison in the same column. So the pKa for an alcohol is usually around 15 or 20. So the lowest pKa is the thiol, followed by the electronegative oxygen. And generally, nitrogen is the next most electronegative atom. But it's not so straightforward here, because this is an sp3 nitrogen, and we're comparing it with an sp3 carbon and an sp carbon. Hybridization is another factor that goes into electronegativity. So if you think about the conjugate base and how well it will stabilize this anion, we need to know which one's more electronegative. Is it sp carbon or is it sp3 nitrogen? And because sp carbon has 50% S character, it is actually more electronegative than sp3 nitrogen, which has 25% S character. Now you just have to memorize that. But what you now know is that when you're comparing electronegativity, it's not just a periodic trend anymore if the hybridizations aren't all the same. In other words, I just want you to know this trend here, where sp3 fluorine is more electronegative than sp3 oxygen. And that is more electronegative than sp carbon. But carbon beats nitrogen when it is sp hybridized at carbon. That's the difference. That's where it breaks the periodic trend. And then sp2 carbon and then sp3 carbon. And we're going to take advantage of that difference in this class in Unit 2 and do reactions where we use sp carbon. But for now, just know these relative pKa's for a proton attached to these neutral atoms. So the pKa of HF is 3.2. If you just think it's 5, that's fine. The alcohol is 15 to 20. An alkyne is 25. An amine is 35. An alkene, sp2 carbon's 45. And an alkane is the least acidic thing you will see in this course. So it's kind of nice they increase by 10 units. And knowing those is a large chunk of the pKa's you're supposed to memorize. But please, please do memorize those indicated pKa's on that chart he gave you. So pKa of the alcohol is lower than the pKa of that terminal alkyne, which is 25. This one is actually a pKa of 40 because this is an allylic sp3 carbon, or there is going to be resonance in the conjugate base, where you can delocalize the anion. So it's not a typical sp3, there is resonance there because of the pi bond. And then you have the amine with a pKa around 35. So most acidic was the thiol, then the alcohol, then the alkyne, then the amine, then the allylic proton. It's very important to know those relative electronegativities and acidities. So the next problem, I'm going to do 3 comparisons of basicity, right? And if you're more comfortable, you can just think about acidity and put a proton on there. But the stronger base is less stable, or it basically desires to lose its negative charge. It's not good at stabilizing that negative charge. So it's very electron rich, and it has a bunch of dense negative charge that needs a proton to counterbalance it. So looking at these 2 oxygen atoms that are both basic, here's the difference. This oxygen is resonance stabilized. Where you can donate a lone pair into the carbonyl and show that the negative charge here is really delocalized so that you have only partial negative charge at each oxygen. Neither one has to bear the burden of all of that formally charged anion, whereas this oxygen of ethoxide is localized. There's no resonance because it's only adjacent to sigma bound atoms or to sp3 atoms. So what that means is this oxygen is truly sp3, whereas this guy is sp2 because it can make a pi bond, or it has a lone pair and is 1 away from a pi bond. That qualifies it as sp2. The other thing that this has going for it is that there is induction, where there's an electronegative oxygen nearby that pulls electrons through sigma bonds and pulls electrons away from that negative charge, helping to spread out this negative charge over a greater volume. Whereas here we have all that negative charge on one atom, where it's very dense. So the stronger base is the atom that is less stable with negative charge because of sp3 hybridization, no resonance, and no induction. So that's this one. Okay, so now each one is the same functional group where you have the same hybridization, resonance, and induction. They're both carboxylates. The only difference is the nearby atom, chlorine versus bromine. And the chlorine is more electronegative than bromine. So the size of chlorine and bromine don't matter because they are not the atom that has the actual negative charge on it. Here it's just a nearby atom. And nearby atom is all about electronegativity, which causes an inductive effect. So the chlorine is going to pull more electron density because it's more electronegative. And therefore it stabilizes the conjugate base. Bromine does not pull as much electron density because it's less electronegative. So more of the negative charge continues to reside in one location, where it's not as spread out. It is more dense negative charge at the oxygen. And therefore, this is the stronger base. If you only have a difference of electronegativity based on the atoms nearby, it's simply inductive effect. And the more electronegative atoms there are, the more acidic or the less basic. Okay. And the more there are, the closer they are, the more they pull electron density. Here it was just a difference of chlorine versus bromine, where bromine was the less electronegative of the two. Okay, so the final one, the difference here is sp carbon versus sp3 carbon. Right, this one has two hydrogens that have not been drawn in, and therefore 4 domains. Sp carbon has 50% S character. More S character means more electronegative, whereas sp3 carbon has 75% S character. So it's, sorry, 75% P character, 25% S character. So it's less electronegative. And therefore, the one that's more electronegative is more stable with a negative charge. So the sp3 is less stable and therefore more reactive, or it wants to get rid of that negative charge and donate it towards a proton. Okay, I'm going to finish by doing these two final acid-base equilibria problems, and then I'll take some questions and I'll send you guys the full solutions and key after that. So in this following problem, the carboxylic acid is the acid with a pKa of approximately 5 at this proton, because it's electronegative, it's got resonance, etc. And the nitrogen is the base. And the nitrogen takes off this proton and leaves a lone pair behind during the acid-base proton transfer. So the nitrogen donates electrons or becomes positively charged. And the pKa of a positively charged ammonium ion, or a nitrogen that's sp3 and positively charged, is around 11. Okay, these are both pKa's that you should know because we're going to see those functional groups a lot. So here, the conjugate base is the carboxylate, and the conjugate acid is the ammonium. And the equilibrium constant is 10 to the difference in pKa's, or 10 to the 6, which means that there are 1,000,000 products for every one pair of reactants, or this favors the products. In other words, this is the weaker side, the weaker conjugate base and the weaker conjugate acid, while the other one is stronger, and the stronger side reacts so that the weaker side predominates at equilibrium. Or these are the major components of the reaction at equilibrium. So acid base is thermodynamic and it's reversible, so whichever side is more stable is the one that predominates. And that stability is a function of this oxygen being electronegative, having resonance, and being sp2 hybridized with an inductive effect nearby. The next one is between an ethoxide base, which has a negative charge, and an acid, alkyne, with a proton of that sp carbon. So here the base gives a lone pair to the proton and leaves a lone pair behind on the carbon, making an alcohol and an acetylide ion. And the alcohol is the conjugate acid with a pKa around 17. And the alkyne is the initial acid with a pKa of 25. So this is the base, and then this is the conjugate base. And the oxygen, as we said, was more electronegative than carbon. So the more stable side is where oxygen has a negative charge. But that's proven by the fact that the equilibrium constant is 10 to the products minus reactants, or 10 to the 17 minus 25. So there are 100 million of these for every one of the products, because it's 1 relative to 10 to the 8th. So this is the weaker side, or the more stable compounds. Okay. So be able to predict those products of acid-base reactions and determine the side that is favored at equilibrium.